This is Dreamtime Science, where we turn fascinating discoveries into bedtime companions. Tonight's journey promises something genuinely intriguing. You know, I've been thinking about how tiny things can sometimes lead to the most unexpected outcomes, like a small ripple turning into a wave. There's something remarkable about the idea that a single flutter of a butterfly's wings might quietly set off a chain of events far away, almost like nature's own whisper of connection. I'm really excited to share how this idea, called the butterfly effect, helps us understand the surprising patterns hidden inside chaos. Should these dreamy explorations accompany your journey to sleep, a gentle like or subscription would be deeply appreciated. What questions about our universe keep you wonderfully curious? Let's prepare for tonight's journey. Find your most comfortable position, let tension float away from your body, and take 3 slow, peaceful breaths. In the hush between midnight and dawn, when the world is neither fully asleep nor fully awake, there exists a moment of trembling possibility. It is in this liminal space that the mind, unshackled by the day's certainties, can meander along stranger paths. Tonight, let us wander through one such path, where mathematics and myth, philosophy and poetry intertwine, a place where the whisper of a butterfly's wings can echo across continents and ages, stirring the air and the imagination alike. Long before equations etched the dance of chaos into chalk dust on blackboards, the ancients intuited that the world was made of interwoven threads, each tugging at the other in ways mysterious and profound. The Greeks spoke of the Moirai, the Fates, 3 sisters spinning, measuring, and snipping the threads of mortal lives, their choices rippling outward with consequences neither mortals nor gods could foresee. In China, the Jade Emperor's court was said to be attentive to the flight of every insect, for each creature's movement was a note in the great symphony of existence. In these stories, no deed was too small, no moment too fleeting, to alter the pattern of the world. But it would take centuries for this intuition to be given the language of science, and for that language to be spoken in whispers that would catch the world's imagination. The phrase butterfly effect entered the lexicon in the most unassuming of ways. Through a talk given by the meteorologist Edward Lorenz in 1972, titled Predictability, Does the Flap of a Butterfly's Wings in Brazil Set Off a Tornado in Texas? Lorenz, however, was not crafting poetry. He was wrestling with the unruly mathematics of weather prediction. Yet, as often happens, the poetry caught fire, and the mathematics smouldered beneath, revealing new worlds of wonder. Let us pause and sit with this image, a butterfly, fragile and iridescent, poised upon a leaf in a sun-dappled glade. Its wings, delicate as tissue and patterned like stained glass, tremble in the warm air. It lifts, flutters, and the air around it stirs. To the eye, this is a moment of ephemeral beauty. To the physicist, it is a question: how far does this ripple travel? How many molecules are nudged? How many currents are born from this single trembling act? The idea at the heart of the butterfly effect is both simple and profoundly unsettling. In certain systems, the tiniest of changes can cascade into outcomes unimaginably vast. This is the province of chaos theory, a branch of mathematics that concerns itself not with disorder, but with the strange, intricate order that arises in systems far from equilibrium. Here, sensitivity is king, a minute variation in the starting point, and the future unfurls along a wildly different course. It is a mistake to think of chaos as mere randomness. The weather, the beating of a human heart, the drip of a leaky faucet, these are not ruled by caprice, but by laws precise and deterministic. And yet, their future is shrouded in unpredictability, not because the laws are unknown, but because the systems themselves are so exquisitely sensitive to initial conditions. This is the great paradox of chaos. The future is written, but the ink is so fine, the paper so delicate, that the faintest touch, a butterfly's wing, a breath, can rewrite the story. In the 1960s, Lawrence was using a primitive computer to model the weather. His equations were simple, just 12 variables meant to capture the looping, swirling patterns of air. One day, wishing to repeat a simulation, he entered the starting values from a printout, rounding them ever so slightly. To his astonishment, the weather patterns produced by the computer diverged rapidly from those of the previous run. A difference in the 6th decimal place, barely the weight of a butterfly, had blossomed into entirely different storms. The implication was clear. The world was not simply unpredictable because it was complex, but because it was fundamentally sensitive. This sensitivity is not limited to the weather. It is the secret pulse beneath the surface of so many things we take for granted. The stock market, the growth of populations, the rhythms of the heart, the flicker of a candle, all can tip from order to chaos with the smallest of nudges. This realization has haunted scientists and philosophers alike, for it suggests that certainty is an illusion, and that the future, while governed by law, is forever out of reach. Yet, chaos theory is not a tale of despair. It is a story of hidden beauty. If you were to plot the path of a double pendulum, a simple device with 2 arms swinging freely, you would see wild, unpredictable motion. But trace this motion in a certain mathematical space, and strange, looping shapes emerge, fractals, infinite in their complexity, self-similar at every scale. The universe, it seems, is not a machine of cogs and wheels, but a garden tangled and lush, each petal and leaf echoing the whole. Pop culture, ever hungry for metaphor, seized upon the butterfly effect with glee. It became a symbol for the unpredictability of life, a shorthand for the way the smallest actions can ripple through time. In Ray Bradbury's A Sound of Thunder, a time traveler steps on a butterfly in the distant past and returns to a world unrecognizable. Films, songs and novels have all taken up the butterfly's standard, weaving its wings into stories of fate and chance. We are drawn to these tales because they mirror our secret hope, that our choices matter, that our lives are not lost in the noise, but are the signal that shapes the future. But the truth, as always, is more subtle. The butterfly effect does not promise that every small thing will change the world, only that in certain systems, under certain conditions, the potential is always there. Most of the time, the air swallows the butterfly's stirrings and the world remains unchanged. Yet sometimes the flutter grows and a storm is born. The ancients, too, told stories of small things with great power. In Norse myth, Loki's mischief, seemingly harmless, unravels the fates of gods and men. In Hindu lore, the gentle drop of Ganga's water upon the earth brings cleansing and transformation. In the Bible, a mustard seed's faith is enough to move mountains. In each of these, we glimpse the intuition that the world is not a closed box, but an unfolding tapestry, sensitive to every touch. Modern science, with its equations and computers, has not dispelled the magic, but has revealed its deeper structure. In the mathematics of chaos, we find fractals, objects whose patterns repeat at every scale. The branching of a tree, the veins in a leaf, the curl of a nautilus shell, all echo the same hidden geometries. Benoit Mandelbrot, the father of fractal geometry, once wrote that clouds are not spheres, mountains are not cones, and lightning does not travel in straight lines. The world, he said, is rough, wild, and beautiful beyond measure. So too is the flow of time. Imagine a stream winding through a meadow. A single pebble, dropped upstream, sends a ripple outward. At first, the disturbance is small, easily lost in the current. But downstream, where the water splits around rocks and eddies spiral, the ripple can grow, splitting and merging, until the whole stream is changed. The butterfly is the pebble, the air is the water, the world is the riverbank, forever reshaped. There is a humility in chaos theory, an acceptance that knowledge is bounded, that prediction has its limits. Yet within those limits there is also a kind of freedom, a sense that the future is not fixed, that possibility blooms at every moment. The butterfly, then, is not just a metaphor for unpredictability, but for hope. In a world that is sensitive to every gesture, every word, every kindness, perhaps we are all butterflies, our wings stirring the air in ways we cannot yet see. The allure of the butterfly effect lies partly in its ambiguity. It is at once a scientific insight and a mirror for our own anxieties and dreams. We fear that the world is out of our control, that our lives are at the mercy of forces too vast to comprehend. And yet we hope that the smallest of our actions might count for something, that a word whispered in the dark might change the course of a life. Chaos theory gives us both, a world unpredictable and a world alive with possibility. In the flickering half-light of the early morning, as the first birds begin to stir, the butterfly is still there, its wings trembling in the dawn. The storm is still far away, the future unwritten. The air is thick with possibility, every moment a point of divergence. Somewhere a child will wake to new dreams. Somewhere else a breeze will rustle the leaves. The world is waiting, sensitive, alive. And so, as the story of chaos moves forward, we find ourselves drawn deeper into the mathematics that underpins this trembling world, into the strange attractors and fractal shapes that shape the weather, the heart, the mind itself. The butterfly's whisper is not the end, but the beginning, a gentle invitation to listen more closely, to watch more keenly, to wonder at the delicate machinery beneath the surface of things. For in the next turn of the tale we will step beyond metaphor and gaze into the heart of chaos itself, where order and disorder spin together in a dance as old as time. The air is trembling, the wings are poised, and the future awaits, just out of reach. In the quiet hours when the world's hurried pulse slows, one can almost hear it, the secret hum beneath reality's skin, the subtle, intricate music of systems entangled beyond easy telling. This is not the stately, predictable ticking of a clockwork universe, but something far more intricate, a web of relations, a tapestry whose threads loop, tangle, and twist in ways that defy our old, linear sensibilities. Step quietly into this deeper chamber of chaos, and you will find yourself drawn into a realm where mathematics reveals not merely numbers and solutions, but exquisite complexities and the very boundaries of human comprehension. There is a certain seduction in the simplicity of linearity. For most of history, scientists and philosophers believed that if you knew the starting conditions of a system and you knew the rules by which it changed, you could predict its future. The universe, in this classical vision, was a grand machine. Every effect had its cause, every action a reaction, every equation a neat, single answer. But beneath this orderly surface, another world awaited discovery, the world of non-linearity, where small nudges could spiral into grand transformations, and the future was not a fixed destination, but a cloud of possibilities. Let us begin not with the most famous equations, but with a humble, almost playful function, the logistic map. At first glance, it is nothing more than an equation, a formula for generating a sequence of numbers, each one a simple function of the last. The logistic map is written as follows: xn plus 1 equal r xn, 1 xn. The uninitiated eye might skim past it, perhaps recalling memories of school algebra and parabolic graphs. Yet, within this unassuming formula lies a universe of chaos and complexity. To understand its magic, imagine a population of rabbits in a closed meadow. Each year, the number of rabbits changes. They multiply, but not limitlessly, for food is finite and space is scarce. The logistic map models this. xn is the population fraction this year. R is a number that describes how quickly the population grows. If R is low, the rabbits breed slowly and the population dwindles. If R is higher, the population stabilizes at a steady level. But as R increases further, something miraculous happens. The steady state gives way to oscillations. First, the population bounces between two values, then 4, then 8, and soon unpredictability takes over. With each increase in R, the dance of numbers becomes more frenetic, more intricate, until it bursts into chaos, a regime where no 2 years are alike, and the population jumps seemingly at random from year to year. Here, in this simple recursion, we encounter the first taste of the nonlinear. Unlike the straight lines and smooth curves of linear equations, nonlinear systems fold back upon themselves. They are recursive, self-referential, and sensitive in ways that defy easy prediction. The logistic map is not just a toy, it is a microcosm of chaos itself, a mathematical echo of the complexity we see in weather, in ecosystems, even in the beating of our hearts. But the logistic map is only the gateway. Beyond it, the mathematics of chaos stretches into even stranger realms. Consider the Lorentz equations, born from the mind of Edward Lorenz, a meteorologist with a penchant for seeking simplicity in the clouds. Lorenz was interested in weather prediction, the archetype of a system where small things matter. He set out to model convection currents in the atmosphere using a set of 3 coupled differential equations. They are deceptively simple in appearance. dx dt equals sy x, di dt equals x rho z, y d's dt xy vz, 3 variables, x, y, and z, each changing in time, each influencing the others. The parameters s, r, and v are constants related to the physical properties of the system. Lorenz set these equations running on one of the earliest computers, hoping for patterns, for stability. What he found instead was a revelation. The system behaved unpredictably, never repeating itself, yet never diverging into meaningless noise. The solutions traced out a delicate butterfly-shaped pattern in 3-dimensional space, a shape now known as the Lorentz attractor. The butterfly, with its wings of infinitesimal detail, became an icon of chaos theory. Its beauty lies not only in its form, but in the lesson it imparts, that even systems governed by strict deterministic rules can produce motion that appears utterly random. The Lorentz attractor is what mathematicians call a strange attractor, a set-in-phase space towards which the system evolves, but never quite repeats, never quite arrives. If you were to start the system twice, with initial conditions a hair's breadth apart, the 2 trajectories would soon diverge entirely, never to meet again. This, then, is one of the most profound discoveries of chaos, the sensitive dependence on initial conditions. In the old linear worldview, a small error in your starting point led to a small error in your answer. In the nonlinear world, a minuscule difference can amplify rapidly until the future becomes unknowable. The metaphor is apt. A butterfly flapping its wings in Brazil, Lorenz mused, might set in motion a tornado in Texas. Not because the butterfly causes the tornado in any direct way, but because the world's web of influences is so tightly interwoven, so delicately balanced, that the tiniest shift can tip the whole system onto a new path. Mathematicians give this sensitivity a formal name: Lyapunov exponents. These numbers measure how quickly nearby trajectories in the system diverge from each other. Positive Lyapunov exponents signal chaos, an exponential growth in uncertainty, a loss of predictive power, no matter how finely you measure. The future in such systems is inherently cloudy. The best you can do is forecast probabilities, not certainties. The mathematics of chaos, intricate as it is, does not stop with population models or weather equations. It extends into the very heart of physics, biology, economics, anywhere feedback and nonlinearity combine. The equations themselves can take many forms: quadratic maps, coupled oscillators, partial differential equations that describe fluids or flames or financial markets. What unites them is their refusal to be tamed by simple analysis. In linear systems, solutions can be written down neatly. In nonlinear systems, the best we can often do is simulate their behavior, watching as complexity unfolds step by step. There is an austere beauty to this new mathematics. It is fractal, self-similar, recursive, endlessly detailed. The logistic map, when plotted for all values of R, reveals the famous bifurcation diagram, a branching tree of possibilities, splitting and splitting until the lines dissolve into a dense, dark forest of chaos. Zoom in on any branch and you find miniature copies of the whole, a hallmark of fractal geometry. The boundary between order and chaos is not sharp, but flecked with islands of stability, windows where regular patterns briefly reappear before dissolving once more into unpredictability. Mandelbrot, another explorer of mathematical wilds, coined the very word fractal to describe these shapes, structures that repeat at every scale, whose boundaries are never smooth, but endlessly wrinkled and complex. The coastline of Britain, he showed, has no well-defined length. The closer you look, the more detail emerges, the longer it becomes. The same principle animates the mathematics of chaos. Patterns within patterns, order tangled with disorder, the infinite hidden within the finite. Within this web of complexity, new concepts arise. The phase space, an abstract landscape where each point represents a possible state of the system, becomes a terrain to be explored, mapped not by roads and rivers, but by trajectories and attractors. Regular systems settle into fixed points or limit cycles, tracing predictable loops. Chaotic systems, by contrast, wander endlessly, never crossing their own paths, yet never escaping the strange attractors that lure them. The phase space becomes a jungle, alive with the ghostly footprints of every possible history. To truly see the mathematics at work, one must become familiar with iteration, repeated application of a rule step by step, each output feeding back as the next input. This is the engine of chaos. Feedback loops, non-linear interactions, the compounding of uncertainty. In the digital age, we can simulate such iteration with ease, letting computers trace out the fates of 1,000 systems, watching as order dissolves, reforms, and dissolves again. Yet the underlying principle is centuries old, glimpsed already in the recursive formulas of Newton and Poincaré, and in the clockwork orbits of the solar system, for even here in the heavens, chaos lurks. The three-body problem, a puzzle as ancient as Newton, asks how three masses, bound by gravity, will move under their mutual influence. For two bodies, the answer is simple: ellipses, circles, perfect repeating paths. For three, the equations become non-linear, and chaos emerges. The planets tug on one another, their orbits twist and wobble, predictability fades. The solar system itself, it turns out, is a chaotic system, its long-term fate balanced on a knife's edge of tiny influences. Non-linearity is not a bug, but the very feature that gives rise to chaos. In a linear equation, the sum of the parts is always equal to the whole. In a non-linear equation, the whole is more or less or different. Emergent properties arise, new patterns form, old patterns dissolve. Feedback loops, positive and negative, create the possibility of wild swings, sudden transitions, spontaneous order from apparent disorder. The mathematics that emerges to describe this world is rich, but also humbling. Exact solutions are rare. Approximation and simulation become our chief tools. Concepts such as bifurcation, a sudden change in system behavior as a parameter passes a critical value, become the signposts of chaos. The logistic map, as ER increases, bifurcates from one solution to two, from two to four, from four to chaos. The language of stability and instability, of attractors and repellers, replaces the old certainties of calculus and Newtonian mechanics. The web of complexity that chaos theory reveals is not merely mathematical but philosophical. It challenges our deepest intuitions about cause and effect, about determinism and randomness. In a chaotic system, the rules are fixed, the laws unchanging, yet the outcomes are unpredictable, as if the universe were rolling dice behind a curtain. The boundaries of what we can know are laid bare. No matter how fine our measurement, how precise our instruments, some futures remain forever out of reach. And yet, within the chaos, there is a strange comfort. The patterns that emerge, fractals, strange attractors, bifurcation diagrams, are not the products of human design, but the deep structure of reality itself. They speak to a hidden order beneath the surface, an order that is not simple, not linear, but infinitely rich. The mathematics of chaos is the mathematics of life, recursive, tangled, and astonishingly beautiful. As you drift within this web, let your thoughts linger on the boundaries of understanding. The equations are not mere symbols, but windows into a world where prediction falters, where knowledge is always partial, always unfolding. Somewhere in the looping arms of a strange attractor, in the branching limbs of a bifurcation tree, or in the endless self-similarity of a fractal, the limits of human reason are written in the language of chaos. The night deepens, and the web of complexity shimmers all around. As one strand trembles, the whole fabric quivers. Perhaps in the next gentle turn we may glimpse how such unfathomable intricacy gives rise to the forms and flows of the natural world, and how in chaos new kinds of order quietly emerge. A faint and restless wind stirs over the landscape of ideas, caressing the surface, and beneath its touch we find the tools of the trade, those ingenious instruments, both physical and mathematical, that have allowed us to reach into the heart of chaos and bring back its secrets. The history of chaos theory is not the story of a single revelation, nor the work of a solitary genius, but a winding path of discovery, marked by moments of clarity and confusion, by accidental insights and determined pursuit. To follow this path is to appreciate the interplay between the abstract beauty of mathematics and the stubborn, unpredictable behavior of the world around us. In the flickering lamplight of the 18th century, before the word chaos had acquired its modern mathematical meaning, scientists had already begun to explore systems whose behavior defied simple prediction. The French mathematician Henri Poincaré, a man of rare intuition and elegance, stands at the threshold of our journey. Poincaré's work at the close of the 19th century planted the seeds that would one day blossom into chaos theory. It began with the three-body problem, a deceptively simple question. Imagine three celestial bodies, say the sun, the earth, and the moon, orbiting and pulling on one another with the invisible threads of gravity. Newton's laws could describe the motion of two such bodies with neat, exact equations. But add a third, and the equations tangle, the motions intertwine, and the future becomes a wild tapestry, impossible to predict with certainty. Poincaré, in his quest to solve the three-body problem, discovered something unsettling. He found that even a minuscule difference in the starting positions or velocities of the bodies could, over time, lead to vastly different orbits. The system was exquisitely sensitive, so much so that prediction became, for practical purposes, impossible. He wrote, "It may happen that small differences in the initial conditions produce very great differences in the final phenomena. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible, and we have the phenomenon of chance." Yet this phenomenon was not true randomness. The system obeyed deterministic laws. It was simply that the future was written in such fine script that no human hand could ever measure its starting point with the infinite precision required. Here, then, was the first inkling of chaos, a deterministic system whose behavior was, in practice, unpredictable, but this insight, though profound, was not yet the chaos theory we know today. For decades, the mathematical community treated such problems as shadows at the edge of understanding, curiosities to be noted and skirted, not explored. It would take the arrival of new tools and a new spirit of curiosity to bring chaos into the light. The 20th century brought with it the rise of computation. The electronic computer, at first a cumbersome and clattering machine, would prove to be the ideal companion for those who wish to explore the labyrinths of nonlinear systems. It is here, in the early 1960s, that we encounter Edward Lorenz, a meteorologist at the Massachusetts Institute of Technology. Lorenz was not seeking chaos. He was interested in the weather, an old and noble pursuit, as ancient as human civilization itself. He wished to understand how air moves, how clouds form, how the wind shifts and the rain falls. To this end, he constructed a simple mathematical model of convection, the process by which warm air rises and cool air sinks, driving the restless motion of the atmosphere. His model consisted of just a few equations, each describing how quantities like temperature and velocity changed over time. One wintry afternoon, Lorenz set his computer to run a simulation. Wanting to check a particular sequence of results, he entered the starting values from an earlier printout, rounded, for convenience, to 3 decimal places rather than the 6 stored in the machine's memory. When the computer finished its run, Lorenz was astonished. The new results, which should have been identical, instead diverged rapidly from the original. The 2 sequences began nearly together, but soon parted ways, like travelers setting off from the same village only to find themselves in different countries. This was no mere artifact of faulty machinery. Lorenz realized that his system was incredibly sensitive to its initial conditions. Even the tiniest change, far smaller than any practical measurement could avoid, would be magnified over time into a completely different outcome. The weather, he saw, was fundamentally unpredictable beyond a certain horizon. This discovery, so simple and so profound, would later be called the butterfly effect, the notion that the flap of a butterfly's wings in Brazil might set off a tornado in Texas. Lorenz's equations, though born of meteorology, soon took on a life of their own. They became the first iconic example of a strange attractor, a set of states towards which a chaotic system tends to evolve, but which takes on a structure of dazzling complexity. When plotted in 3 dimensions, the Lorenz attractor reveals a shape reminiscent of butterfly wings, looping and folding in on itself, never crossing, never quite repeating. The attractor is neither order nor disorder, but a kind of intricate, self-similar dance, a signature of chaos. The tools that revealed this hidden order were both conceptual and practical. The computer became the microscope of chaos theory, allowing scientists to experiment with equations too complex for hand calculation, to watch as patterns emerged from apparent randomness. But the computer alone would not have sufficed without new ways of thinking about systems in motion. One such tool is the phase space, a realm not of ordinary space, but of possibility. In phase space, each point represents a complete state of a system. Every position, every velocity, every variable needed to describe its condition. As the system evolves, its state traces a path through this space, a trajectory that may spiral, loop, or dart unpredictably. For simple systems, these trajectories settle down into fixed points or closed loops, predictable, periodic motion. But in chaotic systems, the paths twist and fold endlessly, never quite retracing themselves, yet always confined to a certain region, the strange attractor. Another indispensable tool is the concept of bifurcation, a kind of mathematical fork in the road. As one varies a parameter in a system, a rate of growth, a strength of interaction, the system may suddenly change its behavior. A single, steady state may split into 2, then 4, then 8, as regularity gives way to chaos. This cascade of bifurcations, known as period doubling, was first mapped in detail by the mathematician Mitchell Feigenbaum in the 1970s. Feigenbaum discovered that the ratio between the intervals of these bifurcations approached a universal constant, now called the Feigenbaum constant, hinting at a deep unity beneath the surface diversity of chaotic systems. To see chaos in action, it is often best to turn not to the vastness of the cosmos or the complexity of the weather, but to the modest setting of a laboratory experiment. One of the most beautiful and accessible examples is the simple dripping faucet, a device so ordinary that its behavior might seem beneath notice. Yet as water accumulates and drips from the spout, the intervals between drops can shift from regular to erratic, depending on the rate of flow. By recording the times between drops and plotting them, experimenters have shown that the pattern can shift from steady rhythm to chaos and back again as the water's trickle is adjusted. Here, in the kitchen sink, lies the same sensitivity to initial conditions, the same intricate dance, as in the orbits of planets or the swirls of the atmosphere. Another classic experiment is the double pendulum, a pendulum with another, smaller pendulum attached to its end. Set it in motion, and its path becomes wild and unpredictable, swinging and tumbling in a manner that seems to have no rhyme or reason. Yet, if you were to record its angles and velocities at each moment and plot them in phase space, you would find the same tangled, looping trajectories, signatures of chaos. In electrical engineering, the Chua circuit has become a laboratory standard. Invented by Leon Chua in the 1980s, it is a simple arrangement of resistors, capacitors, inductors, and a nonlinear element known as the Chua diode. When powered up, the voltages and currents in the circuit can settle into regular oscillations, or, as parameters are tweaked, erupt into chaos. Oscilloscopes reveal waveforms that never repeat, a living portrait of unpredictability drawn in real time by the flow of electrons. But not all of chaos is confined to the laboratory. The beating of the human heart, the flickering of a candle flame, the calling of frogs across a pond at dusk, each can, under the right circumstances, slip into chaos. Researchers have devised clever experiments to tease out these patterns. By measuring the intervals between heartbeats, for instance, and plotting them in phase space, one can sometimes diagnose the onset of dangerous arrhythmias. Here, chaos theory becomes not just a mathematical curiosity, but a tool for understanding and perhaps even saving human lives. The mathematics of chaos is rich and subtle, requiring both precision and imagination. Among its most powerful instruments is the Lyapunov exponent, a measure of how quickly nearby trajectories in phase space diverge. A positive Lyapunov exponent is the hallmark of chaos. It quantifies the exponential sensitivity to initial conditions, the way two nearly identical starting points can end up worlds apart. Calculating these exponents for real systems, be they dripping faucets, swinging pendulums, or populations of animals, allows scientists to distinguish true chaos from mere complexity or noise. Fractals, too, have become indispensable in the study of chaos. These are geometric shapes whose structure is self-similar at every scale. Zoom in and you find smaller copies of the whole repeating endlessly. The boundary of the Mandelbrot set, that iconic fractal discovered by Benoit Mandelbrot in the 1980s, is one of the most famous images in mathematics, a coastline of infinite intricacy, forever unresolved. Fractals appear naturally in chaotic systems, where the strange attractors traced in phase space often have fractal dimensions, neither wholly one-dimensional nor two-dimensional, but something in between, a measure of their infinite detail. The interplay between experiment and theory, between the concrete and the abstract, has driven chaos research forward. In the early days, scientists would sketch attractors by hand, laboriously connecting points on sheets of graph paper. Today, high-speed computers can simulate millions of iterations in the blink of an eye, revealing structures of unimaginable complexity. Yet the essential challenge remains, to find order in disorder, to uncover the rules that govern the unpredictable. It is a challenge that has drawn in researchers from every field: physicists, biologists, economists, engineers, even artists. The tools of chaos theory, phase spaces, bifurcations, Lyapunov exponents, fractals, have become part of the common language of science, used to study everything from the stock market to brain waves, from the growth of tumors to the spread of epidemics. Still, for all its power, chaos theory is not a panacea. It cannot predict the specific path of a hurricane, nor foretell the precise moment a heart will miss a beat. Rather, it teaches humility, that even in a world governed by laws, there are limits to what can be known, horizons beyond which prediction dissolves into possibility. Yet within those limits, chaos theory offers a new kind of understanding, a vision of the world as a tapestry of patterns, ever shifting, ever surprising. So the tools of the trade, those equations, machines, and methods, have not only revealed the existence of chaos, but have given us a way to see it, to measure it, to play with it in the laboratory of the mind and the world. With each new experiment, each new mathematical insight, the boundaries of order and disorder are redrawn, and the realm of chaos becomes, if not tamed, then at least illuminated. And still, questions remain. For if chaos is everywhere, if its patterns are woven through the fabric of nature and mind, what does this mean for the deepest mysteries of existence? How does chaos shape the world we see, the lives we lead, the future we hope to glimpse? These are questions that lead us further into the heart of unpredictability, where the next stage of our journey waits. It's Con. Tours hidden just beyond the veil of the unknown. A gentle hush settles over the mind as we reach the borderlands between mathematics and meaning, where chaos theory is no longer just the property of equations and weather systems, but a lens, a way of gazing at the world, and even at our own tangled hearts. Through the corridors of science we have wandered, tracing the outlines of strange attractors, peering into turbulent rivers and the fluttering atmosphere. Yet all along there has lingered an underlying question. What, after all, does chaos tell us about ourselves? What secrets, what subtle lessons does it whisper about? Our place in a universe that is at once unpredictable and patterned, wild and yet woven with hidden order. Let us drift, then, between mathematics and philosophy, between the restless play of molecules and the stillness of human reflection. For chaos theory is not merely a story about things, weather, fluids, double pendulums, but also a story about how we know, and about the limits and powers of knowledge itself. One cannot contemplate chaos theory long without noticing how it upends the old, comforting ideas of certainty. For centuries, the dream of science was to find, beneath the confusion and change of the world, a steady bedrock, a set of laws from which, if only we had enough data, we could predict the future as surely as the rising of the sun. Newton's universe was a clockwork, each gear pushing the next, every effect the inevitable result of a chain of prior causes. But chaos, with its sensitive dependence on initial conditions, humbles that dream. It tells us, gently but firmly, that the world is not so easily tamed by calculation. In a chaotic system, even the tiniest rounding error, the faintest breath of uncertainty in a starting condition, can swell and spiral into consequences that no mind could foresee. The butterfly flaps its wings in Brazil, and weeks later the skies over Texas thunder and boil. The laws remain as precise as ever, and yet prediction slips through our fingers, as elusive as mist at dawn. This does not mean that chaos is randomness, nor that the world is lawless. The rules are still there, etched in the mathematics of motion, but their unfolding is exquisitely sensitive, so sensitive that no measurement, no matter how careful, can capture the infinite detail required for perfect prediction. Our knowledge is always, inevitably, a little bit blurred, and this blur is enough to unmoor the future from our grasp. Here, in this realization, lies one of the profound philosophical gifts of chaos, the recognition that uncertainty is not always a sign of ignorance or failure, but sometimes a deep property of the world itself. There are truths that cannot be known in advance, futures that cannot be charted with certainty, not because we have made a mistake, but because the fabric of reality itself is woven with unpredictability at its heart. And so, chaos invites us to a new kind of humility. It is a humility not of defeat, but of reverence, a respect for the wildness of the world, for the irreducible complexity of nature, for the limits of our models and the boundaries of our sight. It asks us to relinquish the fantasy of total control and instead to stand in awe at the creative generative powers that unpredictability brings. For unpredictability is not only a source of anxiety. In the living world, it is the wellspring of possibility. Consider the intricate patterns of evolution, the branching, budding tree of life that has, over billions of years, produced the astonishing diversity of creatures on Earth. Here, too, chaos plays its part. Tiny, accidental changes in genes, minute quirks of environment, random encounters between organisms, all feeding into the grand, unpredictable drama of survival and change. The sensitive dependence on initial conditions, so famous in the weather, is mirrored in the history of life itself. Had any small thing been different, the outcomes would have blossomed along other, unimagined paths. The world is not a rigid, predetermined march, but a dance, open, responsive, creative. And in our own lives, too, chaos is present, though often unrecognized. Each day unfolds from 1,000 small choices, each moment shaped by countless influences, some known, most unseen. The course of a life is never perfectly predictable. Friendships, opportunities, loves and losses arrive as if by chance, yet all grow from the subtle interplay of history, circumstance and desire. The story of each person is, in its own way, a chaotic system, sensitive, contingent, irreducibly complex. Does this realization bring comfort or disquiet? Perhaps both in their measure. On the one hand, it is unsettling to know that we cannot control everything, that certainty will always be just out of reach. But there is also in this a liberation, a freedom to accept the mystery and richness of existence, to embrace the unpredictable as a source of wonder rather than fear. Chaos theory, when glimpsed in this light, becomes not only a branch of mathematics, but also a philosophy, a way of living with uncertainty, of honoring complexity, of finding beauty in the unexpected patterns that arise when order and disorder intermingle. It teaches us to look for structure, even where things seem wild, and to expect surprises, even where the rules are strict. Consider for a moment the fractal shapes that chaos reveals, those endlessly branching, self-similar forms that appear in the mathematics of strange attractors, in the outlines of coastlines, in the pattern of leaf veins or networks of rivers. These forms are neither wholly ordered nor completely random. They are poised on the edge, where simplicity and complexity meet. They remind us that beauty often lives not in the extremes, but in the spaces in between, in the quiet tension between pattern and unpredictability. There is a subtle wisdom here, one that echoes through art and poetry as much as through science. The greatest works of music, for instance, balance repetition and novelty, structure and improvisation. A melody that is too predictable becomes dull. One that is too chaotic becomes incomprehensible. It is the interplay, the dance between expectation and surprise that brings vitality and depth. So it is with chaos theory. Its insights do not drive us to despair at the world's unpredictability, nor to the false comfort of rigid control. Instead, they offer a path through the middle, a way of navigating complexity with curiosity and care, of trusting that even in the midst of uncertainty, there are patterns worth seeking, meanings worth making. This attitude, this embrace of complexity, has profound implications for how we approach not only science, but all the tangled questions of human life: politics, economics, medicine, relationships. In each of these domains, the temptation is strong to oversimplify, to imagine that if only we could control the variables, we could guarantee outcomes, solve problems once and for all. Yet chaos theory reminds us that systems can be both lawful and unpredictable, both structured and sensitive, and that our actions may have consequences far beyond what we can foresee. Such a perspective urges caution, but also creativity. It invites us to experiment, to adapt, to respond flexibly when unexpected changes arise. It suggests that wisdom lies not in rigid certainty, but in the capacity to listen, to learn, to respond anew as the world unfolds around us. There is, too, a kind of kinship that chaos theory reveals, a sense that we, like the weather, like the beating heart or the flickering flame, are part of a larger story of emergence, of order arising from disorder, of pattern blooming from unpredictability. The same mathematics that describes the dance of planets and the spirals of galaxies also whispers through the nervous system, animates the rhythms of breath and heartbeat, shapes the branching of neurons and the pulsing of thought. In this way, chaos theory closes the gap between the human and the cosmic, between the mind and the world. It tells us that we are not apart from nature, looking in from outside, but participants in its ongoing improvisation. Our thoughts, our feelings, our societies are themselves complex systems, forever poised on the edge of order and chaos, forever sensitive to the subtlest of influences. Just as a butterfly's wing can tip the balance of a storm, so too can a word, a glance, a moment of kindness ripple outward, shaping lives in ways we cannot predict. The mathematics of chaos hints at a deep connectedness, a web of influence and interdependence that binds all things together in a ceaseless creative unfolding. Yet even as chaos theory reveals these connections, it leaves us with mysteries still unsolved. The equations are elegant, their predictions astonishing, yet there remains a deep well of questions. Why do some systems hover so delicately between order and disorder? What hidden principles shape the emergence of complexity from simplicity? Is there perhaps an underlying unity beneath the wildness, a deeper law yet to be discovered? Such questions linger at the edge of science and philosophy, inviting us to peer further, to wonder more deeply. For all our progress, the world remains richer, stranger, more intricate than any single theory can contain. The dance of chaos and order plays on, and we, as thinking, feeling beings, are swept along in its currents. This is not a reason for despair, but an invitation to curiosity, to humility, to reverence. The mysteries of chaos are not barriers to knowledge, but doorways, gateways to new ways of seeing, new forms of understanding, new possibilities for action and meaning. And so, as we drift toward rest, we may find ourselves pondering the role of chance and necessity, of order and surprise in the tapestry of existence. We may sense, perhaps faintly, the subtle web that links all things, the flutter of wings, the pulse of a heart, the play of thought, the sweep of storm and star. In the gentle embrace of uncertainty, we discover not only the limits of prediction, but also the boundless horizons of possibility. The story of chaos is unfinished, as are all the deepest stories. It is a story not just of science, but of wonder, a reminder that in a world alive with unpredictability, we are both witnesses and participants, both shaped by and shaping the patterns that emerge. As the night deepens and the mind grows quiet, these reflections linger, soft, unresolved, full of promise. The world, it seems, is not a puzzle to be solved, but a mystery to be lived, its patterns emerging, dissolving, and reforming moment by moment in the endless play of chaos and order. And in that play we find our place, uncertain yet wondrous, poised on the edge of knowing and unknowing, forever guided by the subtle currents of possibility that chaos brings. As our journey through the delicate dance of chaos and the whisper of butterfly wings drifts to a close, may you carry this gentle reminder of how small moments ripple through the vast cosmos like a comet tail fading into the hush of space. Rest now in the quiet wonder, and when your dreams seek new mysteries, return to sail once more with me through the endless night of Dreamtime Science.